Hello, my name is Shrikanth. I am from North Carolina State University. In this presentation, I am going to talk to you about our work, Early Lifecycle Software Defect Prediction. I would like to thank my co-authors, Sudeep and Professor Tim Menzies. For decades, software engineering researchers have been looking at ways to predict quality of the software before it is used. A standard approach in this space is to build models based on large volumes of historical data. For example, in case of a GitHub project, to classify commits in the current release, one would build machine learning models based on all the past commits that are labeled either as defective or clean. Many researchers assume that for software analytics, more data is better. We show in this work, at least for defect prediction, this may not be true. Norvik's claim is supported with numerous examples from vision research. While we agree with the y-axis that solution quality could attain a saturation point beyond a certain amount of data, we question the amount on the x-axis. We looked at software engineering literature about sampling policies in defect prediction published in the past decade. We note a remarkably diverse number of sampling policies in the literature that have not been systematically and comparatively evaluated. Not only are researchers hungry for data, but they are also most hungry for the most recent data. We will detail each of these representative sampling policies in the following slides. To assess those sampling policies, we mined numerous popular GitHub projects that are being developed for widely used applications. These projects are non-trivial engineering projects written in widely used programming languages. Those projects are long-running and 20% of their commits on average are defective, and they churn over 3,000 commits. But before we could assess the sampling policies, we wanted to visualize the commits across all the projects we mine, essentially to point to the information-rich region. We observed that most of the defects from those projects occur much earlier. So the takeaway from this slide is that, be it software engineering or mining for gold, it matters where we investigate. Otherwise, our conclusions could be premising on thin ice. Humans learn from experience, and software projects offer experience. Most of the experience occurs early in the project lifecycle, yet developers and researchers make a systematic error. They continue to reason across the lifecycle or from a shallow end of a recent region, which is a problem since there is relatively less experience. This problem can be avoided by learning from experience-rich regions that offer numerous benefits. This explains why many practitioner beliefs on defect prediction tended to decay as the projects progressed. There are some of the data-hungry defect prediction methods where one builds a machine learning model using all past software commits or from recent 3 to 6 months of software commits, or just chosen from the recent release. Over the years, we've bold the assumption that if data is useful, then even more data is much more useful. If most of the defects occur very early in the life cycle, then models learned from the first few months of data should perform just as well as any other data-hungry sampling. Using that result, we introduce a new sampling technique called E that samples 50 commits from the first 4 months of the project lifecycle And to avoid class imbalance problems, equal number of clean and defective commits are chosen. We explored two issues for defect prediction. Is more data better? When is more recent data better than older data? In other words, is there one best sampling policy to build defect predictors? To answer the two research questions, this study compares 5 sampling policies using 6 classifiers in numerous open source projects. We used 7 performance measures to gauge each sampling policy. As mentioned earlier, all our data comes from open source GitHub projects. We used Commit Guru to mine the process metrics and defect information from these projects. But data from Commit Guru does not contain release information, which we extract separately from the project tags using GitHub APIs. To compare sampling policies, we run all pairs experiments in 5 steps. Each step is a defect prediction model built using one of the 6 classifiers using data sampled from one of the 5 policies discussed earlier. Then we use that model to test on all future releases. Then we gauge using 6 performance measures, and those distributions of those test release scores is analyzed statistically using the Scott-Knott test. Whenever a project has a new release, it means that more data, that is commits, is accumulated. Thus, one needs to retrain their machine learning models if they are using data-hungry sampling policies. On the other hand, stop early policy E uses a fixed number of 50 commits that would imply the model need not be retrained, which is a huge benefit that enables practitioners to offer stable conclusions across the software lifecycle. This table shows results of 24 defect prediction models tested in all project releases. No policy and learner pair wins 7 out of 7 times on all performance criteria. But we can say it is useful to apply CFS and logistic regression. To answer this question, is more data better? Our data hungriest sampling policy all that basically ingests all commits from the past loses on most criteria. E that uses 25 defective and 25 clean commits selected at random from the first 4 months of the project lifecycle is competitive with the rest of the sampling policies. When is more recent data better than older data? This table shows results of 12 defect prediction models tested in all project releases. If recent data is comparatively more informative than older data, then defect predictors built on recent data, that is RR, should outperform predictors built on much older data, that is E. However, we see that E and RR seems to perform almost the same. So we conclude that recency-based methods perform no better than the results from early lifecycle predictors. To reiterate, many researchers assume that for software analytics, more data is better. At least for defect predictors, this may not be true. Issues with conclusion instability disappear if early in the life cycle we can learn a predictive model that is effective for rest of the project. In summary, before assuming complexity, it is prudent to check the raw data, looking for shortcuts that can simplify the analysis. We hope these results inspire other researchers to adopt a simplicity-first approach to their work. Thank you for watching my presentation.
From North Carolina State University. Oh, we have a guest. Hi, Tim.
From me today.
Nice to see you.
I beg your pardon. Federica, how are you? Have you
I'm
won?
good. I'm good.
Really?
We have 3 seconds. We're gonna be live. Hi, everyone. Welcome to the session Data Prediction, Data Issues, and Bug Classification. We are with the authors of the first paper in this session, Early Lifecycle Software Data Prediction, Why, How. So Shrikanth and a team from North Carolina State University are two of the authors of the paper, and are very happy to take your question. Let me read. The first one is from James Bolden. So do your conclusion depend on the time series looking like the one on your slides, where most development was done early and relatively few commits are currently being made?
Yeah, yes, pretty much. So,
and we're finding that to be a crazy common pattern. And we can tell you that the paper the paper had popular projects with more than 1,000 stars. We've looked at unpopular projects with less than 1,000 stars, and it's exactly the same pattern. So we think there's a previously unreported, very general pattern.
So what would be your suggestion to look to build prediction model to look always at the early stages?
Shrikanth?
Yeah. So as per these patterns is early stages, but more generally what we would like to say is wherever the data is rich, please focus on that. Like look where your data is rich. The pattern says it's always early because chaos happens in the project often in the early stages and it becomes stable. So yes.
And I know that people like Federica have debated different, and myself have debated different sampling policies. If you have multiple releases, do you train on release I-1 and test on release I? Based on this paper, we'd have to deprecate that, which something I've done a lot, by the way. It's like a lot of the stuff based on late life cycle might be completely erroneous, where the data is so thin, there's nothing to learn.
Yeah, I've seen a few papers coming up in this with this respect in the last couple of years, and one will be the next paper. So I think this session can bring to fruitful discussion around the topic. I think we don't still have the right answer, but it's good to see the community working towards it. I'll read couple of more questions. I mean, I have plenty of questions myself, but I guess I have to prioritize others. In the graph, you showed that most defects occur in the first 50 months. How do you justify the first 4 months threshold? How have you picked the first 4 months?
Simply, what we did was we tried various months and we kept shrinking the window until it stopped working. So the moment it became 4 months and all that we needed was 4 months, that was effective for all the state-of-the-art policies that we found.
And I think a follow-up question from Peter is how you have selected, why 50 data points sampled over these 4 months? Why just 50? Why not 100? I mean, is 50 enough to train a classifier? That sounds a bit low.
Yeah, so I would like to answer in 2 ways this question.
Sure.
2008, Dr. Menzies' paper had 50 data points. And recently, in a seminal paper of heterogeneous defect prediction, Nam and others had 50 data points. And what we did is I started with 600 data points. I reduced it to 300, 150, 50. And less than 50, it stopped working. So I stopped at 50, where 25 were defective and 25 were clean. Yep.
So this, when you did the higher numbers, the results were similar, better. I mean, shall we consider 50 as the results you got with 50 a lower bound?
That's in the paper, and there's a follow-up paper. Okay. If you email us, we can send you the TSE submission we put out last Friday, which we're happy to share with everyone that emails us. And we're actually doing better in some respects by reasoning only from the early life cycle.
Okay.
It's like feature selection stuff. We can now build a model that's general across 250 projects using just that early life cycle data, and that works much better than lots of other things.
Okay, so we look forward to read more on your TSC extension about this. There's a question from Shenyon Chang. Why do you think that more data don't improve the prediction performance? What's your insight on that, given what you've observed?
Why do you think it does? It would.
That using more data doesn't improve.
Why? I mean, if there's a signal in the data and the well's shallow, once you get to the bottom of the well, you can keep digging if you want, but there's no more information. You know, what if, you know?
I think what you're saying is that you find this signal at the very early stages. So it doesn't really matter if you add much more data that has been produced later on during the project.
Early in the life cycle, you're making more mistakes. The ratio of buggy commits to non-buggy commits is highest and most constant. That's an important information source. Later on in the life cycle, you're working where the air's thinner. You're on thin ice. You know, there's less information around.
Yeah, I can believe this could generalize to probably even other open source projects. I know you mind lots.
Perhaps other domains.
Yeah, other domains. Do you think this would be the case also in industry, given your experience with software companies, especially for very large projects like at Facebook, at Google, where their software might not be that stable over time? Like may keep growing a lot, but there won't just be a big boom and then.
I mean, in my personal experience, there's a lot of difference between starting something from scratch and a huge feature request. A feature request may not, because the framework is already ready. But when you're starting a project from scratch, people keep running around in teams and there's a lot of chaos. That's when the most defects probably are injected, and most experience is also generated. So, yes.
But what I'd also say to Federica is, when you say Facebook, the software is growing, Facebook is not one software.
Yeah.
People work on separate projects. So what I'd like to know is whether our profile that there's more information gain, more information acquirable early life cycle, where that occurs in-house. I think that's a very reasonable question.
Yeah.
You're a very reasonable woman.
Okay, I think there are no other questions from the audience. We still have a few minutes. May I ask a more technical question? Because I read the paper, I got pretty curious, given we shared this passion for the web prediction. So I haven't quite understood the old policy. Yeah.
Let's ask the cross-project question.
Yeah, okay. Have you tested on cross-project?
Shrikanth, you tell us about the last 2 weeks of your life writing that TSC paper.
Yeah, a lot of overleaf errors and LaTeX errors. Yes, we've tested it on cross project, and that results holds surprisingly even there. Even the same 50 data points suffices, and in fact, we have even more improvements over that. We've introduced a policy called E+, that only looks at 2 features instead of 14 features, and surprisingly, it suffices.
Well, but it's not just the features, because I don't want to go back to the Martin Shepard days of lines of code as a surrogate for everything else. It's 2 features collected early in the life cycle.
Correct.
So there's been a lot of prior talk about what features matter the most, and I'm going, well, that's a context-independent statement. Why don't you ask what features matter the most at the time when they're most collected? You know, yeah. But the cross-project stuff, we've benchmarked it against TCA+, a whole bunch of other cross-project methods, and we really are saying that learn from the first 150, you can build a model that works across 250 projects.
Yes.
Okay. Would you reveal us what are these 2 features, so we have to read the TSC paper?
Shrikanth?
Sorry?
They're 2 size-based measures, right?
We have 30 seconds.
Yes.
Hi,